Hello again, my dear friends. Nice to meet you again. And we're going to start lesson number 12, which talks about stacks again. Well, last time we introduced the concept of stacks, and we talked about the different operations we could perform on stacks. Developed basically all prototypes about the functions we're going to develop. And today we're going to continue on the same direction. And this time we're going to talk about more operations on stacks. Basically, we're going to implement the functions which we introduced the last time. And then, as you all remember, we implemented stacks using arrays. And now we're going to look at a different way of implementing stacks, and a more efficient way basically, and that's using dynamic data structures rather than static. Okay, let's see. Last time when we started, we talked about the basic three functions, how to check whether the stack is full or not, how to check whether it's empty or not, and in the first place, how to create a stack. Let's continue with the other operations. The first function we're going to cover today is the push function. If you all remember from the prototype we talked about the last time, we said pushing an element to a stack means putting that entry at the top of stack. And as a prerequisite for this function to work, we said the stack has to exist as a must, and then it's not full. So we're going to be using here the function stack full. So the answer for that, if yes, then I cannot do anything, and I have to return indicating that the stack was full. Otherwise, if it's not full, then I hope to successfully put the argument that I have on top of the stack, adjust the stack pointer, which points to the top of stack accordingly. Okay, let's see how that's going to be implemented. It's very simple and straightforward. As we mentioned earlier, this function is going to be of type void, so it's not going to return a value per se, but rather it's going to take the item of type stack entry and insert it on top of the stack s. So I'm passing here a pointer to the stack s and the item itself, which I'm going to add on top. Item in here is passed by value because I'm not going to change its value as a matter of fact, but rather I'm just going to take whatever it has and place it in here. Item after I return is going to return its value. It doesn't matter. Okay, and let's see how it works. Well, in the implementation here, to double check, I'm checking again whether the stack is full or not. So I can use this function right away without asking the question, is the stack full or not? However, we can just write it down right away without this decision statement, assuming that I'm gonna perform this check before I start. Okay, let's do it this way. That's very simple and straightforward right away. So the first thing I'm gonna do, I'm gonna make a call to this function, stack full. And I'm passing to it that my stack is, which I'm getting from the calling statement. Okay, so if you all remember, the return value for this function is actually of type Boolean, and this is going to be 1, that's true, if the stack is full. If the stack is full, then I cannot add any entries to the stack. And that means I'm going to be returning back with some error statement saying that the stack is full. So in here, I'm assuming that there is some sort of a function called error, okay? And I'm passing a message in here saying that stack is full, just an indicator. So I'm assuming that this kind of function is basically going to display a message to the user showing the user that the stack you're attempting to add items to is really full, and to return. Okay? Well, that's in case the stack was full. However, if the stack is not full, so else, if the value here is 0, that means there is a room for a new entry to be placed on top of stack. In that case, what I'm going to do, I'm just going to take item and place it on top of the stack. Here's my stack again. It was like an array, as I said, pointed by pointer s, and that's my stack. However, inside here, I already have some items, and top is pointing to the last valid entry in this stack. So what I'm going to do now, since there is room, I'm going to take whatever in item and place it on top of stack. And after that, I need to advance top to point to the next item. So this is like two statements in one. So basically what we're saying in here is take item, which is the new entry I want to add, and then place it in the stack at top. Okay? And then after you do that, make top point to the next item. So here was the top of stack. This is already full, okay? And I'm ready to add a new entry in here. So what I'm doing, take this, place it in this location, and then make top of stack to point to the next entry. And it's very important to mention in here two things actually, and that's two ways of handling stacks, as a matter of fact. The first is, and that's with regard to the top. I could make top always point to an empty location, so whenever I push to the stack, I place right away the item to the top of stack and then I advance it. That's one way of doing it. So top, usually in this case, points to the next empty location in the stack. That's one way of doing it. So when you push, you put the item right away on top of stack, and then you advance your top of stack pointer. Another way, I will make top point to the last full entry in the stack. Okay? So if this entry was full, then in this, according to this, I will make top pointing here. So when I push, I need first to advance the top of stack one position forward and then put the entry. Okay, so it depends upon the implementation. Both implementations are used in real practice, and it depends upon the environment you're working in. So it depends upon the application. You select, if you're the developer of the programmer, to use this way of handling the stack or this way, and they both work, and they both have been used widely. So in our case here, we're assuming that top is pointing to an empty location. So what you're going to do, you're going to place item first at this location, and then you're going to advance your pointer to point to the next available location. Okay? That's very simple and very straightforward. After that, you can go home safely and return. The other function is to pop from the stack. Popping from the stack means retrieving data out of the stack. So first, you have to make sure that the stack is not empty, otherwise there will be an underflow, as we mentioned in the last class. And so the prerequisite for this, or the precondition, is that the stack already exists, of course, and it's not empty, because an attempt to bring something from an empty stack means underflow, and that's an error. So again, I have to check first to call the function which we called stack empty, which we developed last time. And if it's yes, empty, I have to return some sort of an error indicating that there is an underflow, no items to retrieve. If the stack is not empty, then we will retrieve the item on top of the stack. Okay, and again, this function is of type void, as I'm not returning anything per se, but rather all I'm doing is inside the function parameters. So this time I'm passing a pointer to item, and this item is going to carry actually the content of the entry on top of the stack. And this time we're passing a pointer to it rather than item itself by value, because its value is going to change. And this is obvious because I'm going to put something in the item when I return. And that's why the asterisk here is very important, as a matter of fact. And then the second parameter is, of course, the stack is itself. And I'm assuming that it has been already initialized and created properly. Okay, so to double check, I'm starting again with this if statement saying that is stack empty? If yes, if this returns a 1, that means no entries in the stack, then I'm going to be displaying a message to the user saying that the stack is empty and I don't have any items to give you. And again, I'm calling this function, which I assume written somehow, somewhere, so that it tells the user the case we're at. Well, but if the stack is not empty, and that means we have some data to retrieve, and this comes here, then I'm going to put in this item entry, in the location where item points to, whatever I have on top of stack after I increment this pointer. So I'm going to go back, right? And again, I'm assuming that top is pointing to the last empty location, all right, to the one after the full. So it is the first scenario we talked about when I was talking here. Okay, so top always points to an empty location rather than a full one. So what I need to do when I want to retrieve an information from the stack, here's my stack. It has already some elements inside it, and top is pointing here, and this is empty now. Okay, here's S, and here's top. So to retrieve, I need first, step number 1, to get top equals to top minus 1. And then number 2, get whatever data, what we call data entry, pointed by top, and place it in item. Of course, in the location pointed by item. These are just pseudocode kind of statements. So that's what we're doing. I will first decrement the position and then take whatever data in there in my stack, take that entry and place it in the memory where item is pointing. Okay? And then my stack is ready and I return. Item now contains whatever data on top of stack. The third function is to clear stack. Well, clearing stack means flushing the content of the stack, right? Throw all entries in the stack. Well, let's think for a second. Since we're talking about a pointer that always points to the top of stack, do I have physically to throw all entries in the stack in the air and put zeros or something else in that place? Well, not necessarily. All I can say is make the top of stack points to the first entry in the stack. That means, by default, these entries are considered as invalid data, because if they're valid, then top will be pointing to them, to the last one of these entries. Okay? So by making the pointer top of stack pointing to the first entry in the stack, I'm saying that whatever you have in here is just rubbish. All right, non-valid data, and you can overwrite it anytime you like. And this is simply flushing. This is simply clearing the content. So clearing the content doesn't necessarily mean to wipe it out, to throw it away, but rather simply make your pointer to point to the top, to the first entry in the stack. That way, you're making the rest of the space available for user, assuming that you don't have valid data in the whole stack. And that's the way we're implementing this. So basically, if this is my stack, again, all right, pointed by S, and I already have some data in here, okay, and this is top of stack, pointing here, then when I say flush or clear the stack, means just migrate this and make it point to here. And that means implicitly, this is not valid, not valid, not valid, not valid, same as the rest of the locations in here. So all I'm going to do when I clear the stack is simply make top of stack point to 0. Okay, the precondition for this is that stack S already exists and it's not empty, has been initialized, let's put it this way. As a result of this function, all entries in the stack are removed and the stack is cleared. We're not going to physically remove them. However, logically, since we're always point to the stack and we consider the last entry in the stack is pointed by top, so when I take it to the beginning of the stack, that means the stack is empty. And that's what we're doing in here. It's of type void again, clear stack, and it takes as an input the stack S. And simply, all I'm going to say, stack arrow top equals to 0. Make the stack pointing, the top of stack pointing to this location. Okay? Very simple, very straightforward. Going around the thing. Okay? And that's physically what happens really in computers. When we clear the content of any variable, as a matter of fact, in the memory, physically we don't clear, we don't wipe, we don't throw the content of the location. We're just saying that this location no more contains valid data. And that's it. So you can overwrite on top of that data. Same thing when you delete, as a matter of fact, from the hard drive, from the hard disk, or when you delete from any of means of the memory that you have. So all it says when you clear it is that just make that space available to the user. Okay? So you move your marker to where you have valid data to the beginning, and that indicates that whatever you have in here is actually invalid. Very simple and straightforward. Stack size. In many cases, I would like to know how many items do I have in the stack. Like I know the maximum size is like 100, let's say, but how many items are really living inside the stack? Do I have all 100 full, or do I have 20, 30, 50? I would like to know, because based on that, I'm going to make some other calculations. All right? So I would like to develop a function which returns to me the number of items contained basically in a stack. Well, again, the assumption we're making in all of these functions is that top of stack always point to the, not the last entry, but the empty one, the first empty after last. Okay, and this is very helpful in our and very straightforward because we're using C, and this starts counting from 0. So when I say top equals, in this case, let's say 0, 1, 2, 3, 4, 5. So when I say the size is 5, actually, yes, I'm referring to 5 entries in here, starting from 0 to 4. Okay. So basically, instead of running a counter, which is going to start from the very beginning and add up as long as I see valid items in here, basically, I'm just going to return the value of top of stack. Okay? So this has an index of 5, right? So this has index 0, index 1, 2, 3, 4, and 5. So top is now sitting here, pointing the value of top is actually 5. Okay? And physically, since it is standing here, then I have locations from 0 to 4 all full. And that means I have 5 items. So basically, just return the index here, which is top, and that is what gives the size of the array, or the size of the stack. So basically, this function returns the size of the stack. It takes as an input and as an assumption the stack S, which is assumed to be already created, and it has some items inside it. And it returns the number of entries in the stack. It returns a value of type integer, and that indicates the size of the stack, number of entries in there. And it's called stack size, not clear stack. This is a mistake. I will fix this after we finish with the class, but please make a note that this is stack size. So I'm going to write it all down here so you would notice. It's called integer stack size, and it takes as input the stack is as pointer to it, as a matter of fact. And then simply, what I'm going to do inside here is just return stack arrow top. So I'm returning as an integer value the index top as my return value in here. And as I said, this top actually, which is the index within the array, actually represents the number of items that I already have before that. So basically, this gives me the size of the stack, and that's exactly what I want. Okay, so please note again that the name of this function is stack size and not, as it says here, clear stack. This is taken from the previous slide, and I'll make sure to fix it once I'm done with this presentation. Other functions, hope not to find other mistakes like this one. Okay, stack top. Well, stack top, in many applications, as we said earlier, I would like to look and process actually the item on top of stack, but without actually popping it from the stack. I would like to keep the stack unchanged, the same. I just want to take a copy of the last entry and process it outside. Okay? So nothing will happen to the stack in terms of number of items and the whatever data contained in these items, but rather I would like just to make a copy outside the stack and process that item the way I like. Okay? So this returns the item at the top of stack without changing the stack itself. Prerequisite for this, I'm assuming that S already exists and has been initialized. And of course, it's not empty. Otherwise, I'm going to have an underflow. The outcome of this is that item, which is some secondary temporary variable outside, which I want to use, is going to get whatever on top of stack, just a copy of it, okay, without being removed. I'm not going to remove it. So top of stack is going to stay where it's pointing. Okay, let's see. It retains a value of type void called stack top, and it takes two arguments, two parameters. The first parameter is item, which is of type stack entry, a pointer to that because we're going to change its value. It's going to be loaded from the stack, and that's why I have this asterisk here. And of course, the stack itself or a pointer to that stack, S. Okay? And to make sure that the stack is not empty, I'm going to check again and call this function stack empty. Is the stack S empty? If yes, 1, then there is an error. I cannot retrieve, I cannot copy anything from that stack. There is no valid data in there. Okay? So I'm calling this function error. Else, if there are items, then please take whatever you have on top of stack without changing it, without decrementing it. Keep it where it is. Keep top pointing to the same location. Just take whatever in there, the entry, okay, at that position, top, and put it in the memory pointed by item. So basically, here's my stack. S, right? And I already have, as I said, items in here. Top is pointing here. Okay, and this is the last full entry in this stack. Okay, so all I'm going to do is, and it depends upon the implementation, the way I'm implementing it in this case is that I'm assuming that I have valid data in here. Again, you can use this or that. It's not a big deal. But the idea is that I have in the memory somewhere down here a location pointed by item. The size of this location is the same as the size of the entry in here. So what I'm going to do, just make a copy of this and place it in here. Keep whatever data in here as is. Keep top pointing to the same location. Don't touch it. Just make a copy of it and place it in here. Later on in my program, I'm going to be working on this location rather than the stack itself. Okay? And this depends, of course, upon the application we're developing, whether to physically pop the content of the stack or just make a copy of the top of stack. So that's up to the application, and it depends upon the situation we're working on. Okay. One last function is left in the group of functions we talked about last time, which is how to traverse a stack. Basically, as we said, traversing a stack means I'm going to visit every single entry in the stack and modify it, do something about the entries in there. Okay? That's very simple and straightforward to implement it. I'm going to keep it as an exercise for you. We always, teachers, do the easy part and leave the hard part for you guys. So that's one of the hard parts. I'm just joking in here. It's very simple and straightforward. You try to do it at home, and please try to implement it on the computer and make sure that you're doing it the right way. So basically, what we're supposed to do in here, in this little homework, is that I have already this stack S. The assumption is that the stack S already exists and has been created, and it's not empty as well. You better check for that if you would like to. All right, and we're having top pointing here, and I have elements inside it. So what I want you to do is to go and visit every entry in here and change its contents. Let's say the entries in here represent student structures, and I'm going to make a very nice example. You all like it. You all talk always about grades, and you all want your grades to be 100. Okay, how about that? The entries in here are of type structure. So struct student record, whatever the name of it, and what it has inside it, name, and that's of type character, integer ID. We have developed this structure before, I believe, and then grade in here, float, let's say, grade. Okay? So what I want you to do is to write a program which defines the node in the stack to be of this type, and then to write a visit function or traverse function which is going to go through all entries in the stack, and these entries represent all of the students in our class, okay, and give 5 grades bonus to everyone. So whatever grades they have, go to visit every one of the nodes in the stack and go to the grade. Okay, so structure arrow grade or dot grade. It depends upon the way you're going to pass it, and I assume you're going to all use pointers. Okay, and do grade equals grade plus 5. That means we're visiting all entries in the stack. Okay, so I'm going to keep this as an exercise for you to work on. Excellent. Let's develop a skeleton for a main program that manipulates stacks. Basically, I would like to have some sort of a menu-driven program that will basically give the user the choice to select among the different functions. The functions, whatever we have developed so far, to check if the stack is full, check if the stack is empty, push to the stack, pop from the stack, traverse the stack, check the size of the stack, and so forth. Okay, so to develop a program like that, we're going to call it in here stack manipulation. Okay, I'm going to include the standard I/O because I'm going to ask the user to input his choice, and I'm going to display some results on the screen. And then I'm going to start my main program. My main program has, as an initialization here, a stack pointer called myStack of type stack. So that basically to start a stack, all right? And then I'm going to use some local variables called I and value. We're going to see their usage as we move on with the program. Okay, the first thing I'm going to do, I'm going to create the stack called myStack. So I'm calling this function create stack, which we've developed last time. And I'm passing to it myStack. So myStack after return is gonna point to a structure, array structure, like this with certain maximum number of entries. Okay, and this is called myStack, this way. Okay, and it has as many entries as the max, whatever max we defined. Okay. What am I going to do next? Well, I'm saying while 1. That means while true. Basically, keep going on again and again. Never stop unless you physically exit the program through the operating system. Okay? And in real-time systems, we always find statements like these. Always do. That's what it says. Okay. What I'm doing, I'm saying printf stack manipulation. Okay, so each time it starts, it's gonna display on the screen stack manipulation like a title, and new line to give space for a nice looking kind of function. And then I'm saying printf one.push text, no line, 2 for pop, 3 for top and end. I'm not implementing everything in here. You can, of course, implement all functions we have covered in this class and the previous class, in this lesson and the previous lesson, okay, all together. In this simple example, I'm just showing 3 different choices. I'm gonna either push to the stack, pop from the stack, or copy the element on top of stack, or just return, exit. All right, so this is my menu basically in here, and I'm asking the user to enter his choice. So he's going to enter his choice I, okay? And I could be either 1, 2, 3, or 4, okay? The user hits one of these. Well, now I'm going to use the famous switch statement in C. Switch on I. Case of 1, if I equals to 1, that means push according to the stack, right? To the menu, right? So basically, what I'm saying is enter the value you want me to push to the stack. Enter the item you want me to push to the stack. Basically, we could, for simplicity, consider our stack to be just list of integers. No big deal. And that's why we're taking this value to be an integer. And that's what we defined. So I'm asking the user to enter the value he needs to push to the stack. Okay, user enters the data here. So I'm calling the function push, which we developed a few minutes ago. And I'm passing value and my stack. Of course, I need to pass, this is pointer of type pointer, and it has been already been defined as pointer to stack. Okay? So upon return from this, value is going to go to top of stack, and top stack is going to be adjusted accordingly. And then for the user, I'm printing a statement saying the value, this value has been pushed into the stack, and break, get out of the switch statement. Case of 2, and that's the case of pop. Then basically, I'm gonna call the function pop, all right, and I'm passing to it my stack and a pointer to value. So basically, whatever on top of my stack is gonna be retrieved and placed in value. Okay, and top of stack is going to be adjusted accordingly. And then after that, I'm printing to the user a statement indicating that I have popped value from the stack, and I break. Case of 3, I want to retrieve what's on top of stack without altering the stack itself. So it's just copying. So basically, I'm going to call this function stack top. I'm passing an address to value and my stack. So basically, I'm going to take whatever on top, make a copy of it, and place it in the memory at value. All right? My stack is going to stay the same, unchanged. And again, I'm printing to the user a statement. The value on top, okay, is so-and-so is value. And I break. Case of 4, this is my exiting condition. I say if you get to here, if the user enters 4, just return, exit the program. And that's basically the program. Very simple, very easy to understand, and very easy to develop as well. So as another exercise, if you please, I would like you to extend this program to consider other functions that we have talked about so far in this class and the previous class. Okay? Like to check if the stack is full or not, check if it's empty or not, check, count the number of entries in the stack, and so forth. Whatever functions we have developed so far. This way, if you do this, and I encourage you highly to do it, okay, this way, the whole subject of stacks is going to be very simple and very easy for you, and you can manipulate the stacks the way you like, and you're going to feel very confident about the topic. Okay, stack initialization revisited. We would like to revisit again the stack initialization. In the previous lesson, we implemented the stacks using arrays. And of course, in earlier classes, we said, well, arrays are not actually the best choice for structures like these, because simply I could reserve a number of entries in my stack and realize in the middle of my program that I'm not going to use that much of memory. So why waste it? Or I could realize in the middle of my program is that I don't have enough spaces. My stack gets full very fast and I need to insert more entries. Okay, so if that's the case, then the other solution, the other alternative is definitely a dynamic allocation rather than static allocation. And we would like to revisit the static initialization process using dynamic allocation rather than static allocation. Okay, so based on this, all subsequent functions will assume the following declaration. Dynamic is definitely better and it's more practical, as I mentioned. Hence, we will revisit these definitions and modify these definitions accordingly. Okay, and that means we have to revisit every function which we have developed so far to take this into account. We're going to start from the definition of the stack. We define the stack to have a structure like this. Integer top, which is a pointer to top of stack, and it's basically indexed within the array. But at the other time, we had stack entry to be a matrix. So in the previous definition, we had something like stack entry of max stack. We had something like this. So already reserved maximum number of entries in here. This time, I don't want this because I don't know whether this is going to be sufficient or not, whether this is too much, and whether I need it all or not. And instead, I'm just going to create a pointer in here. All right? And I'm going to put the max stack in here. Okay? So that's the major change in the stack structure declaration statement. Okay, based on this, let's go to the initialization. I'm going to only cover in this lesson the stack initialization function, and I'll leave for you the other implementations, which pretty much goes straightforward like this one, as you're going to see. This type, create stack, is going to return a pointer to stack rather than returning void. Okay, so this is the major change. So the return value is of type stack pointer, and it takes as an input the maximum number of elements, and that's going to be one of the entries in the structure. No preconditions. After this, stack will be created and assigned as empty. Let's see real quick how this goes. Very simple, straightforward. Okay, here it is. I'm going to define a local variable of type pointer to stack called s. Okay, and then I'm going to use the malloc function. Okay, and I'm going to allocate in the memory the size of stack, size of pointer stack, and instead of return it as a type void, I'm casting it to be of type stack pointer. Okay, so after successful return of this malloc, I will have a pointer in the memory called s. Okay, that's gonna later on point to my stack. So if this succeeds, then I'm going to have that pointer. If s is null, then malloc was not able actually to allocate the memory, and that's why I'm going to return null, and that indicates that I could not allocate enough memory. However, upon successful, as I said, I'm going to initialize it now. Well, initialize it, make top pointing to 0. Very simple. And put max stack equals to the maximum number of elements passed as a parameter in this function. And now I need to create allocate in the memory size for the stack itself, for the entries in the stack. So what I'm saying in here, again, entry, okay, malloc, maximum number of elements times the size of stack entry. So that many entries, okay, depending upon the maximum number, and make the type of this type, stack entry, pointer to stack entry. So again, if I don't succeed, that means I could not find enough memory, and in that case, before I return, I have to free the pointer to s itself, and that's why I'm saying free s and I return null. Okay, that's non-successful. However, if I succeed, then I already created a pointer for S, and I reserved in the memory enough space of this size, okay, and I'm making S pointing to that, all right? So return that S as my return value. So now my return value is actually a pointer which points to a block of memory called stack with enough number of entries that can accommodate these many. What I want you now to do is to go and visit every function that we have covered. Take into consideration now the new way of defining the stack using the dynamic structures rather than the simple static structures. Okay, that's very easy and very straightforward. Minor changes need to be done. And remember to use dynamic allocation rather than static. Use malloc and use the free function. Okay, this pretty much covers all I want to talk about stacks. Hope you liked it. And to find more material and other exercises, you can go to the internet, click on the UNINETTUNO site, and click on the MidNetU project, and you're going to find lots of stuff. Thank you very much, and I'll see you next time. Bye.